joining us for the last SIG webinar of the year. For those who are new to the webinar series, there's a slight delay in the audio and video feed, so please be patient when asking questions. Today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. Today we have Professor Jon Aurnou. Jon received his PhD from Johns Hopkins University and currently heads the Spin Lab at UCLA, where he leads a team of researchers interested in fluid and magnetohydrodynamics. Jon combines experimental and numerical simulations to understand the fluid processes in planetary cores and atmospheres. Today, Jon will be discussing his research and the efforts of SIG's Geodynamo Working Group to benchmark current dynamo codes and develop the next generation of massively parallel geodynamo codes. It's all yours,
Okay.
Jon.
Thanks very much, Lorraine. Can you hear me? I hope well. Anyways, thanks again for having me to give this talk. The outline of the talk is that first I'm just going to go over the current paradigm for understanding planetary dynamo physics and dynamo modeling. Then I'm going to discuss some shortcomings of that framework. Then I'll talk about how I think we get around that. For me, that's the need to develop dynamo models that are fully turbulent and rather more extreme in their capabilities. And finally, I'll discuss how to create those models through CIG's Dynamo Development Project. Okay, so first our current framework. So here you see an image of Earth's magnetic field showing the radial component of the magnetic field on Earth's core mantle boundary. And what you see is that the field is predominantly dipolar, with flux actually emerging from the hemisphere, coming around and entering back into the core in the northern hemisphere. So it's a dipole, and it's fairly well aligned with the rotation axis of the planet. In addition, the field has a number of really strong both high and low latitude flux patches, with most of the dipole field energy coming from the high latitude flux patches. And those high latitude flux patches are situated just outside the tangent cylinder, where the tangent cylinder is the imaginary right cylinder that circumscribes the solid inner core. And roughly those large high latitude flux patches, you could fit about 6 to 8 of them around the tangent cylinder, which means they're approximately 1,000 kilometers in size. Okay, so the core is really a rather remote system. There's a whole, about more than 2,000 kilometers of mantle between us and the core. And so it's a remote system, and to evaluate its physics and its properties and behaviors correctly, we need to accurately model that system. And I would argue in the past roughly 20 years, we've had really some incredible successes in modeling dynamo action. And by that I mean we're solving for Earth's core geodynamo. We're modeling this coupled system between Navier-Stokes, the momentum equation, the induction equation, and the energy equation, typically for a Boussinesq fluid. And these are massively coupled nonlinear equations, so it's a fairly complex problem. And what's maybe the key is that to date, what we can do is we can have inductive similarity in the models, which means that if we non-dimensionalize this equation, the induction equation, which describes the evolution of the magnetic field vector B, then we see that there's only one non-dimensional parameter, Rm, the magnetic Reynolds number, and it describes the ratio of induction, which is the curl cross U cross B term, the first term on the right-hand side of the equation, versus the diffusion equation, the second term on the right-hand side. And in Earth's core, the magnetic Reynolds number has a value of about 1,000, and we can also reach that value in the numerical models. So we have similarity in the essential large-scale magnetohydrodynamics. That's fairly wonderful. And so what do we get out of that? Well, it means basically we can create very nice numerical models, such as this one from Krista Soderlund. And this image shows the radial magnetic field on the outer boundary of her model. And you can see there is some large-scale flux patches on the tangent cylinder, and also some complexity of the magnetic field near the equatorial plane as well. Nice thing about the numerical models is we can look under, under the surface of that boundary, which we can't do with Earth. We can't actually look underneath the core mantle boundary. In the models we can, and we can see the interior flows. So we can see, here's an image of the Z vorticity in Krista's model. So that's the swirling motions of the fluid along the direction of the rotation axis, the Z vector or the Z hat direction. And you can see there are these large-scale columns that are fairly well aligned with the rotation axis. And this then leads to schematics such as this very nice image from Uli Christensen from 2011, in which it's argued that large-scale structures, large-scale columns, such as those in the models, explain the basic magnetohydrodynamics underlying geodynamo generation. So if we now port one of those columns to an image from Julien Aubert, then we see where there's the big column in his model. If you look underneath that, there's magnetic field shown by these kind of fat white lines. The magnetic field is fairly well aligned with the column, and at the top and bottom it kind of twists around. It's twisted by the flows just underneath the boundary. And that produces these green and yellow magnetic flux patches shown in the image. So affiliated with the columns are flux patches at the ends. So we can then port that back to Uli's image, and in addition to those large-scale columns, we expect to see large-scale flux patches like we see on Earth. So that's what I would call success. We are able to generate numerical models that create well-aligned large-scale flux patches in the models, such as we observe in the magnetic field. Okay, so that leads then to an extrapolation often made in the field that the columns that exist in the models also exist in the core. And there's a further extrapolation, which is that the physics in the models also extrapolates to the core. Again, we can match the morphology of the core rather well, so that suggests maybe that we're matching the physics. And I want to question those two extrapolations in the next part of the talk. I'll do that briefly. But that is, for me, the current framework of dynamo physics. We can create really rather impressive models that can explain the basic morphology we see in Earth's magnetic field. And the question I now want to get to is, are we able to make the extrapolations about core physics from those models that we do right now? And I'm going to say we have to be cautious when we do that, because mainly there are some problems with the columns. In particular, the models are too viscous, and I think that changes some of the way we see the effects of the columns. In addition, with work from my laboratory at UCLA, we've argued strongly that the columns probably aren't that stable. And in addition, if you use real liquid metals, they're even less stable. I won't really talk about points 2 and 3 to save time. I'll just talk about point 1 in this talk. So let's talk about having overly strong viscosity in these models. Well, to understand that, let's first look at the effects, basically rotating convection columns, and let's first talk about rotation. Non-dimensionally, we talk about the effects of rotation by scaling the viscous force with the Coriolis force. And that ratio is, in fluid dynamics, called the Ekman number. And so it's the viscosity nu over omega, the angular rotation rate, times basically the vertical height of the system squared. And so that tells us how strong, effectively, rotation is relative to viscosity, or really viscosity relative to rotation. And then to set up convection, we have another non-dimensional number called the Rayleigh number, which gives us the buoyancy force in the system. And so this image shows some quote-unquote pink fluid at the bottom, blue at the top. I'm assuming the pink stuff is less dense than the blue stuff, and that will tend to drive convection. The light stuff will want to float up. And in a rapidly rotating system, it ends up that convection doesn't start until you force the fluid hard enough to basically overcome the rotational constraint. So the rotation tends to lock the fluid up and turn it into kind of a fluid gyroscope that doesn't want to turn over in any way. And so the faster the rotation rate, the larger the buoyancy force you have to impose to drive convection. And once you do get convection to occur in a rapidly rotating system, you find that at first onsets is these very narrow columns. So the width of the column scales, again, with the Ekman number. The Ekman number typically is very small in a rapidly rotating system. And the width of these columns goes as Ekman to the 1/3. The height of them is the whole height of the container. And so very different from non-rotating convection. In rotating systems, you expect these columnar modes at the onset of convection, and they sure should be skinny. Okay, so here's an image from Eric King from 2013, and this is showing typical horizontal length divided by the size of the tank, so L over some depth D. That's on the y-axis, and on the x-axis is the Ekman number. And we see that L, this black solid line, shows L does scale roughly as Ekman to the 1/3. The boxes are a whole bunch of different simulations of rotating convection. Eric and Bruce Buffett followed that with another paper in which they did a similar analysis for planetary dynamo models, and they found the same scaling. So the typical length scale of the structures in these models is indeed goes as Ekman to the 1/3. And the median value for the dynamo models is about an Ekman number of about 10 to the -4, maybe even a little higher value. And if you then look over where does that correspond to for a horizontal width of the columns, you get a value of about 10 to the -1. So I would argue we presently, since we've done almost all our simulations, planetary dynamo simulations, at an Ekman number of 10 to the -4, our intuition is about there, and we expect roughly about 10 structures, right? L over D is about 1/10, so we expect about 10 structures in these models. And so if we then say the models typically have this median value Ekman number of 10 to the -4, Ekman to the 1/3 scaling gives us a typical column width of 1/10, then that gives us about the size of structure we see in the schematic, and it roughly pertains to what we see in the models as well. So that all makes sense. And now the issue is that when we try to make this same argument to explain the models and do that for Earth's core, then we see that Earth's core has a much lower Ekman number. The Ekman number in Earth's core is about 10 to the -15, which means that the width of the columns would then be about 1/100,000th their height. So they'd be very tall. You'd predict that they'd, again, still be about the height of the core, but they'd be incredibly narrow. And actually, this image here shows them about 1,000 times too wide. If they made them the theoretical prescription for their width, they just don't show up at all. It's narrower than a pixel on this screen. So then the fundamental, or one of the fundamental problems with columns in the models, well, first of all, they were great in the models. These Ekman to the 1/3 scale columns are able to generate large-scale magnetic flux patches, and they do actually a marvelous job. The issue is when you try to export or extrapolate that same argument to a planetary core, that same Ekman to the 1/3 scaling predicts columns that are about 10 meters in width. So super tall and so thin. And in that case, the local magnetic Reynolds number for those structures is significantly less than 1. And it's not clear that these columns would even produce magnetic fields. It might actually be that they're just purely magnetically diffusive structures. In addition, such skinny structures, 10 meters wide, they're really small. We can never observe the direct signature of those, so they can't be used to explain the large-scale flux patches observed in Earth's magnetic field, which is effectively what is done presently. And in addition, these model-style columns, if you extrapolate that physics to planetary cores, they're probably magnetically ineffective or transparent, right? They just don't induce any field. Okay. The other 2 points I'm not going to address here in order to save time. And instead, I'll just sum up that one, I skipped from points 2 and 3 that I didn't actually discuss. I don't believe the columns, these 10 meter by roughly 2,000 kilometer tall columns, are likely to be stable. They probably actually become three-dimensional and devolve into quasi-geostrophic turbulence. And that's especially true in liquid metals where the inertial terms are more relevant. However, if those columns did exist and you extrapolate them to planetary settings, they're so skinny that they really can explain the large-scale flux patches that we seek to describe. Okay, so what do we do? That's what I'm calling the problems with the framework. How do we get around that? It is a problem. So this image here on the left, again, shows something similar to the very nice schematic from Uli Christensen. It shows in present-day laminar models, you have these really big columns that I would call laminar. They're forming right at the onset of convection. There's no turbulence in the system. And they are roughly at the scale that we need in order to explain the kind of large-scale structures you see in the magnetic fields. But as I've tried to argue, they don't extrapolate well. And instead, what I'm suggesting is that we need to be developing fully turbulent multi-scale models where this convective length scale, which should go as Ekman to the 1/3, it should be tiny. In fact, even here it's kind of big. But it should be becoming much, 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 much smaller than the typical system length scale of the spherical shell. And out of that turbulence, we need to emerge larger scale structures that can generate large scale flux patches. Now, is that just a pie in the sky dream of mine, like so many others? And I want to suggest that it's not that crazy of an idea. Here's an image of a rotating convection simulation, or actually two different movies from the same simulation. These are produced by Keith Julian's group at the University of Colorado. This was published in Julian 2012, and more recently from his group from Rubio 2014. And what they're doing is they're simulating rotating convection in the asymptotic limit of rapid rotation. So when they do that, they can still, one, generate three-dimensional flows. The columns do become unstable, as I suggested earlier. And from that quasi-geostrophic, rapidly rotating turbulence emerges large-scale structures. So let's look at, this is a movie showing their perturbation temperature field. It's strongly three-dimensional, but I hope you can also see there's also a large-scale component of that. So from the small-scale quasi-geostrophic convection emerges large-scale structure. So now we're looking, in addition to that oblique view, below we see a top view of the depth-averaged Z vorticity. And we see, viewed from above, you see two huge vortices forming from the small-scale turbulence. And so this is called an inverse cascade, where from small-scale structure emerges large-scale coherent structure. And so the convective scale is, again, very small here. It's much smaller than the box size. And out comes a larger scale turbulent structure. What sets the turbulence scale in these simulations is actually the box size. If you can afford to do a bigger box, you get a bigger structure. In addition, you might notice that the two vortices are opposing. There's one red cyclonic vortex and one blue anticyclonic vortex. And that occurs basically because the system is conserving its angular momentum. Okay, now those results are from these asymptotically reduced models, but I want to point out that the same physics emerges in direct numerical simulations. This is a box model from Stefan Stelmach, so it's rapidly rotating Boussinesq convection at an Ekman number of 10 to the minus 7, so about 3 orders of magnitude weaker viscous force relative to Coriolis force in this simulation than in the median Dynamo models, which are at about 10 to the minus 4. So if we go down about 3 orders of magnitude in this parameter, I'm predicting that we'll start to see interesting large-scale structures emerge. And again, you can see these are very similar results to what Keith Julian's group got from the asymptotically reduced theory. This is at a finite Rossby number, which means there's turbulence, but the turbulence is strongly affected by rotation. And in Keith Julian's, in the rapidly reduced system, the Rossby number is effectively heading towards zero, or is asymptoting towards zero. And so you can have this turbulence that's completely dominated by rotation, and yet still out of that you can get large-scale structures. Okay, so what about dynamo models? Are there any dynamo models that act at all like this? Well, there's really only one that I know of, honestly, and it's a model carried out by Andrei Sheko, who's a graduate student at ETH. And he's run this model at an Ekman number of about 3 times 10 to the minus 7. And he's run it on, I think it's almost 1,000 processors for a year and a half. So for a long, long time, using a large supercomputing grant in Switzerland. And what you see is, you see small-scale columns that roughly scale as Ekman to the 1/3, and they're not coherent. They don't stretch from boundary to boundary. In general, you'll note that they're breaking up before they go stretch all the way across the fluid shell. Here we're looking at a meridional slice, and we're looking at the radial velocity along that slice. And what you see, I made a red box, red dash box right in the inside the northern tangent cylinder, and you'll see every now and then that a large-scale vortex passes through there right now. And so out of these smaller scale columns emerges some larger scale structures. You'll see some others in other parts of the shell, but I think that's the best example. So I think out of turbulence you can get large scale structures. And I also think simultaneously that the small scale structures, as we head towards core parameters, this is an Ekman number of 3 times 10 to the minus 7. Earth's core is roughly 8 orders of magnitude lower in Ekman numbers, so these columns would be getting smaller and smaller and smaller. And so now we look at the magnetic field in his model. One, you don't see any columns. In fact, if I showed you this movie before I showed you the flow field, you probably wouldn't infer there are any columns at all in the flow field. And so there's a nice dipole magnetic field, but it's decoupled from the columns directly. And now if we look at the magnetic field on the orbital boundary, we see again a nice dipole. We see some interesting large-scale vortices forming inside the tangent cylinder at high latitudes. And we might also see some interesting structures extending out from the tangent cylinder. But I don't see any obvious flux bundles associated with large-scale vortices yet. Not located outside the tangent cylinder like we see in Earth's magnetic field. If I take a snapshot, I do see some large-scale flux patches. It's just not clear they're axially aligned, but they have any coherence across the equator. It's not so clear they're yet affiliated with large-scale vortices like we, at least presently, want to argue for Earth. Maybe that argument's wrong. I just know we don't see that here. So this is the one, what I would argue, strongly turbulent dynamo model that's out there. Very low viscous forces. And so then you get small-scale columns. They rarely extend across the fluid shell. They don't obviously produce any individual magnetic signatures like they do in the Ekman roughly 10 to the minus 4 experiments. There are some large-scale turbulent flow structures that appear to form some big vortices inside the tangent cylinder at very high latitudes. And maybe there are baroclinic instabilities extending outside the tangent cylinder. So maybe the tangent cylinder becomes unstable to what are called baroclinic instabilities. That may produce some larger scale turbulent structures roughly in the right location, just outside the tangent cylinder location. Nice. Okay. What does that produce? It produces a dipolar magnetic field, and as I just got stuck trying to say, possibly with flux patches located near the tangent cylinder. Are those flux patches axially aligned like I don't know if we argue or we assume occurs for Earth's core, but anyways, I'm not sure we explain all the data all that well yet, but we do start to see the emergence of a lot of different, and I would say transformatively different physics that better resembles planetary core dynamics. However, this is just a single case, and as I've been trying to get across, it's suggestive of a bunch of things. but again, a single case. And I don't think we can say all that much definitively with just a single case. We need to have surveys, and we need to have systematics to really know what's going on. Okay, so I've tried to argue then that the present-day models are far too viscous and laminar. We need turbulent dynamos with multi-scale physics, and I think one of the directions that is very well suited to do that is CIG's ability to develop large-scale coding frameworks. And so the Dynamo working group, since about February 2013, has been carrying out a new Dynamo development project. And I just want to discuss that with the time I have left. So the working group's myself and Ben Brown from Kavli Institute and Colorado, Bruce Buffett from Berkeley, Gary Glatzmeyer from Santa Cruz, Nick Featherstone at Boulder and CIG, Eric Hyen at CIG, Lorraine Huang at CIG, Hiro Matsui at CIG, Peter Olson at Johns Hopkins, and Sabina Stanley at the University of Toronto. And I just want to go through their 4 points I want to discuss. One, the prior CIG code prior to this development project, the 2 codes that are presently being developed, Calypso and Rayleigh, and then lastly, a community-wide benchmark exercise that we are carrying out. So, prior CIG Dynamo code is the MAG code, which was actually Gary Glatzmeyer's code that was then modified by Uli Christensen and Peter Olson. It is a serial code, so it runs on a single processor. It's very well documented and benchmarked, and it's good for studying laminar dynamo action. So here's a nice image from a movie from Peter Olson, and in this relatively standard simulation from MAG, the Ekman number has a value of 6 times 10 to the minus 3, so roughly almost 10 to the minus 2. And the Reynolds number of the flow then is about 8. And that's why I'm saying these are basically laminar simulations. It's actually difficult to have a fluid dynamics problem even in a cup of water or a cup of honey having a Reynolds number of order 8. So these are really viscous simulations. And so I think that is a nice code in that it solves all the equations correctly, but I don't know that it extrapolates well to planets. And I think we can make great strides by developing better codes for CIG and for the community. And so the first of those is the Calypso code, developed by Hiro Matsui and Bruce Buffett. Lead developer is Hiro Matsui. This is an OpenMP MPI parallelized Fortran 90 code, pseudospectral. Again, good documentation available on the CIG webpage, and it's documented and benchmarked. Right? Version 1.0 was put out in September 2013, so it's available for download at any point in time. And this code solves Boosanesque equations for rotating convection-driven dynamo action in a spherical shell geometry. As I mentioned before, F90, OpenMP, MPI. In the summer of 2014, so within the next couple months, there will be, I think it's version 1.1, I forget exactly if that's the right numbering, but the code will then be able to solve for 2 different buoyancy sources, so 2 different sources of buoyancy diffusing on different timescales, such as thermal buoyancy and compositional buoyancy, and that's interesting for core problems. And I believe the goal is for winter 2015 for this code to be able to solve a full sphere dynamo problem, so no inner core, which is a very interesting problem for Earth, where it may be that we have a relatively young inner core, so why is it we appear to have a very long-lived dynamo? And if that's the case, it means we've been able to have a dynamo naturally emerge from a full sphere core geometry very easily. In addition, that version 2.0 will also have non-uniform thermal and compositional boundary conditions. So then we can study the effects of non-uniform boundary conditions, as is likely relevant in terrestrial bodies, for instance. This image shows the scaling properties of Calypso. We see the red curve is for a problem with maximum spherical harmonic degree of 47. The red curve with open red circles. And on the other side of the diagram is, again, a red curve. But with closed red circles, that corresponds to an Lmax, a maximum spherical harmonic degree of almost 500. The dashed lines show the ideal scaling for each problem size, and you can see as we're going to bigger problems, the code is scaling better. And for instance, on the largest size problem here, Lmax of almost 500, the code scales well to almost ideally to about 800 cores, and it's pretty darn good out to beyond 1,000 cores. Here's a test run Hero did, showing a Dynamo model with, there we go, with an Ekman number of about 2 × 10⁻⁵. And this goes up to about 300 spherical harmonics for resolution. And this was solved using 480 cores on Stampede in a 5-day just test run, just to see how it works. You can see here that the columnar structures. This map shows the magnetic field on the outer boundary of the model. The columns are still mapping into the magnetic field for these parameter values, but I do think you can see that the columns are getting significantly smaller, and as we head down to smaller and smaller values, those columns are, I think, going to fall out of what's directly observable in the field. Okay, how's this code disseminated? One, you can go right to the CIG site up here, just above in the upper right. There's the link to the web page where you can download the code. This was presented at Fall AGU. In addition, there's going to be a Dynamo workshop. I'll discuss that later in the fall this year. At the CIDR meeting this summer at Santa Barbara, there'll be a tutorial on how to run the code. And in addition, at the ELSI meeting preceding this summer's SETI meeting in Tokyo, there will be a tutorial at Tokyo Tech, again, on how to run this particular code. Okay, so that's the Calypso code developed under this Dynamo development project. And in addition, there's another code being developed, this time by Nick Featherstone. And this is we're calling this the Rayleigh code, and it's based on another pseudospectral code developed originally, what really is originally, again, Gary Glatzmeyer's original model, but this was developed in the solar community, largely by Nick, along with Tom Clooney. And this code scales up to about 30,000 cores, the solar code. And so the Rayleigh code is trying to harvest the work of the solar community and produce a geo/solar dynamo model that has comparable scaling up to about 30,000 to hopefully even higher numbers of cores. Essential to this idea is that it's got a very modular framework, so it can accept different equation sets, handle different equations of state, Boussinesq versus anelastic, for instance, and even do different geometries such as spherical, shell versus Cartesian. So we can really crosstalk many, many different problems and across many different communities, we hope, with this code. Initial release date is probably late 2014 or early 2015. However, Nick already has a working spherical shell dynamo model that he's successfully benchmarked. And just in brief, Here's an image of non-rotating, non-magnetic convection, so the canonical problem of Rayleigh-Bénard convection in a spherical shell with a Rayleigh number of about 10 to the 7. Spherical harmonics go up to a value, maximum spherical harmonic, 380, 756 points in radius, using radially finite differences. 4,000, roughly 4,000 cores were used to solve this problem, and it ran for about 12 hours. And so that shows the transient where warm fluid erupts effectively off the inner spherical boundary and heads out to the outer boundary, and then spreads out, cools off, and heads back into the interior. So that looks rather interesting. And now let's compare that to a rapidly rotating case. So for this next movie, we now show for a rotation axis inclined by roughly, let's say, 20 degrees and pointed slightly obliquely just out of the page, we now have a rotating case with an Ekman number of 10 to the minus 5. Everything else is about the same. Oh, I got the number of radial points backwards. It's 756 radial points in this problem. And it was, I think, 512 in the other problem. But Nick, you can fix that if you will. Let me know. Again, though, about 4,000 cores, and this was run for about 6 hours. And you see the fluid dynamics has fundamentally changed between these large-scale radial upwellings for the non-rotating case. Now all the fluid dynamics is noting the effects of rotation, and they're happening on these skinny columns that are all aligned, again, with the rotation axis. It looks here like there's some, again, rather significant vortical flow near the North Pole. And the color scale, as in the earlier movie, was temperature perturbations relative to the radial temperature field. And so really different response, of course, in a rotating simulation, small scale columns. Okay. How does this code scale? I forget what size problems these are, but I think we're going from about 124 points cubed to about, in blue, to about 1,000 cubed in red. And you see very good scaling, well past 1,000 cores for the first 3 cases. On the red case, the largest size problem, it's the scaling's tailing off, and that appears to be because of a cache problem that Nick says can be fixed, can be addressed. So this code is scaling rather well too. And that's the present state of the Rayleigh code. Nick will, I think, next be adding anelasticity. It has already been benchmarked, and that brings me to the next problem, which is, oh yeah, no, it's not. I forgot this point. So yeah, actually this should have been at least its own slide. I forgot. Apologies. So one thing you'll see from both the examples I gave from the Calypso code and from the Rayleigh code are that, we did these test problems at an Ekman number of about 10 to the minus 5. And of course, these experiments aren't cheap. So we really need significant computing resources, even to show how well these codes scale. And I think also to do proof of concept hero runs. For instance, none of our preliminary test cases match up to what Andrei Shako's done running for a year and a half on the Swiss national machine. So we need to get some big time for this project to really prove to the community that these codes, yes, they'll be publicly available, but we also want to prove just how fast they are and just how well they scale. And that's requiring, for instance, we're going to put in an insight proposal in the next couple months to try to get some really big allocations to really see that these codes perform as we are engineering them to do. Okay. Lastly, community benchmark exercise. That's been run by the CIG Dynamo working group. In address of this question, what method or what techniques are best suited for next generation geodynamo models? Not the ones we're building right now, which are aiming to reach tens of thousands of cores, but instead, how do we in the next 10 to 20 years be carrying out dynamos on, let's say, hundreds of thousands of cores or even more? And so this exercise is carrying out two things. First, we're asking for all the different dynamo models in the community to carry out accuracy benchmarks to see how well they're working for a couple different magnetic boundary conditions. And then CIG itself is performing, in a sense, a standardized benchmark exercise in which all the different codes are going to be run on the same environment using the Stampede machine in Texas, and all the codes will be on the same massively parallel device, and we'll see how they then scale for performance to see who runs not just accurately but fastest. And many of the codes are accurate. The question is, how do we run really, really fast so that we can address the right physics and be in this robust, turbulent framework for the dynamo physics, which I'm arguing is what's relevant to planetary and stellar settings. So at present, we have accuracy results from 13 different models, and I think there are one or two more coming in. You can see listed around here all the different universities taking part, but we've got codes that do horizontal spherical harmonic expansions and radial Chebyshev, spherical harmonics and finite difference in radius, spherical harmonics and compact finite difference in radius, one finite element method, and one which is finite elements in meridional slices and Fourier in azimuth. Right now, so those are all the accuracy results that are in, and right now Eric Hyen and Hiro Matsui are setting up to carry out the performance exercises on Stampede. And then we'll see, again, we know how accurate these models are now, how fast do they run, and which ones are best to propagate into the future. We'll be talking about this at the Fall 2014 Dynamo Workshop, organized by CIG. It'll be October 2nd and 3rd, and I believe it'll be at NCAR, with Mark Misch from NCAR as the local host there. The focus of the meeting will be on basically the cross comparison between all these different benchmarks and the implications of the benchmark results for future dynamo development. And where the idea again is to figure out which are the best avenues to be developing in the future for peta and exascale devices. Okay, and so that was my actually rather brief summary of all the different topics being carried out by the CIG Dynamo Working Group, and I hope I've gotten across to you. We have a very beautiful framework for modeling planetary dynamos, but there are significant limitations with those models. It looks like they may not very robustly or predictively scale down to planetary settings. I think we need multi-scale, fully turbulent, rapidly rotating dynamo models. That means we need big computing, and CIG now has put out in the last year and a half the Calypso model, which can be run by anyone, scaling for already shown to scale to over 1,000 cores, and the Rayleigh code that is still in development that will scale likely to tens of thousands of cores. Who can I thank working on this project? Again, the entire Dynamo Working Group has done a huge amount of work in the past roughly 2 years. And I also want to thank, so on that note in particular, Hiro Matsui with his work on Calypso and Nick Featherstone working on the Rayleigh code. And then I also just wanted to thank for a lot of the science images that were in the first, I'd say, 2/3 of this talk. I want to thank Keith Julian's group at Boulder, some images from Stefan Stelmach. I think actually I cut out all the results from the lab, so Adolfo and John Sheng didn't give us any images, but I cut them out about 20 minutes ago to save time. And then we saw some images from Eric King and Krista Soderlund, so I want to thank them as well. And I think that's all I have for today. Thanks very much, and if you have any questions, please ask away.
Thanks, John. The floor is now open for questions. I think everybody will soon have their microphones enabled, so if you have any questions for John, just chime on in, or if you're microphone shy, just type in the chat box.
And I can't see the chat box, I don't think. So if you do chat box it, Lorraine, can you just read it to me? Or I guess I could leave full screen.
Yeah. I don't see anybody typing in right now.
So I was so clear that there are no questions?
Absolutely. Everybody was stunned by your results.
It is so relaxing.
Well, John, thank you so much for today's webinar and also for leading the geodynamo benchmarking effort. This is going to be really exciting in the fall to see the results of both the performance and the accuracy benchmark. I know a lot of us can't wait to see who will take home the prize, so to speak.
Mm-hmm.
This wraps up this year's SIG webinar series. Thank you all for attending. Please check our website in late summer for next year's webinar series, which will continue on the second Thursday of the month beginning in October. Our first webinar will be October the 9th. I don't see any questions coming in, so thank you everybody and have a great afternoon.
Thank you, Lorraine.